Hi guys, I'm Rylan. Excited to tell you about ZEP today. Excited also to be presenting at PapersWeLove. I love to come to these things. They're like my favorite event in the city. So thank you guys for having me and for putting this on. Thank you, Datadog. Okay, so ZEP. ZEP is a memory architecture, temporally aware knowledge graph for AI agent memory. One of many architectures that sort of exploded over the last few years as LLMs have become more popular. I've gotten really into AI memory, and so that's how I ended up giving this talk. So a little bit about me. My name is Rylan. I co-founded a company called Crate.fm. After that, I led product for a while in insurance tech, and then right now I'm co-founding a company called Retriever, and we actually use AI memory for product analytics, essentially. But the net here is, for the last year, I've been obsessed with AI memory, both what it can do, for businesses, but also too what it can do personally. The idea that we can remember everything we read and be able to access that in a really easy way, I think is very exciting. And so that's what got me into it and excited to talk about it today. So I'm going to steal from Nathan. He gave a talk on liquid types earlier this year at PapersWeLove. He had this context, text, subtext framework that I thought was really interesting. So we're going to talk about the context of AI memory. After we talk context, we will actually jump into the paper itself, and then we'll talk some subtext on the paper. So let's jump into context. What is AI memory and why do we need it, especially in LLM systems? Well, our LLMs are stateless today. At test time, an LLM can access only its parametric knowledge, which is the information stored in its weights from pre-training, and the tokens in its context window, so the information provided in its prompt. I've denoted this with red and green, red being fixed, static, parametric knowledge that we can't affect when we run an LLM, green being the dynamic context window input that we can affect when we run an LLM. And so the idea of AI memory is really focused on this green side. What can we do here to make LLMs less stateless and give them contextual awareness over multiple calls? And this just illustrates that further. If we had 4 calls, they are entirely discrete. They do not know that the other exists unless we start to connect the context window inputs with something like AI memory. So, like I said, AI memory enables LLMs to store, retrieve, and use information over time and persist context across long horizons, multiple sessions, multiple months, multiple years. Over time, we get more accurate, contextually relevant responses and an overall better user experience. Any questions up to this point? No? Okay. So honing in now on the part that we can affect, which is this sort of dynamic context window input, we can do things like input prompt texts, retrieve documents, chat history, system instructions, and there are a whole lot of things that have been done to kind of new fields, context engineering, prompt engineering, memory specifically, that really all focus on what we can do with the context window input. What I've put here on the side of the screen is actually the output of ZEP. When you run their memory system, this is the result. And it just gives you an idea of really what we're trying to do here is hydrate that context window with as much information as we can so that the LLM gives a really rich and contextually relevant response when it does its generation. And we're going to talk more about this. We'll see this later, but just wanted to kind of give you an idea of where we're going and why we're going there with this context window input. So things we can build with AI memory. For all of us who are engineers, a coding copilot that adopts to our conventions, naming patterns, and architectural opinions. I really want this. I don't really have this yet, so I'm excited about that. But a personal assistant that understands us, a tutor that tracks our mastery level, and then some really interesting ones, like a lifelong system that grows alongside you, accumulating context over a multi-year horizon, or personal context and preferences that follow you across apps and devices. So I think in a long term, AI memory presents a lot of really interesting opportunities. And again, a lot of the reason I'm interested in it. So where are we today in the AI memory space? The answer is it's kind of a mess. There's a lot going on. which is cool because if you're into reading papers, it's fun. There's a lot of different architectures, a lot of different approaches to solving this problem, many different benchmarks, and we start to now see different architectures from OpenAI, Anthropic, and other companies. So it's kind of a scattered space right now. I don't think it's a solved space, and there's a lot of interesting technology being built today. Also, it's noisy enough that we now have memory companies kind of taking jabs at other memory companies. This is an actual blog post, Lies, Damn Lies and Statistics, from Zep calling out another competitor of theirs, MEM0. It's just kind of a fun space to follow along with, both from a technical point of view, but also there's stuff like this. So that's the context. Any questions before we jump into the text itself? But that's a little bit about the space. Okay. So the text, starting with the abstract, I went in and highlighted some of the stuff that I thought was important here. Number one, Zep outperforms the current state-of-the-art system when this paper was published, which at the time was a paper called MEMGPT, which is today a company called Leda. Specifically, they outperform in the Deep Memory Retrieval DMR benchmark, which again at the time was sort of the state-of-the-art benchmark. So we do dynamic knowledge integration. It's a temporally aware knowledge graph that maintains historical relationships, and we're going to see how here in a little bit. Also, too, they established the LongMemEval, or they use the LongMemEval here, which they assert is more accurate and more relevant than the DMR, Deep Memory Retrieval. We'll look at that a little bit. And they do well on that LongMemEval benchmark. So that's the abstract. Can you guys raise hands who actually read the paper? Awesome, awesome, awesome. You guys, not so awesome. There you go. But all good, because what we're going to do is actually just like walk through the paper. So starting with the abstract, we're going to go section by section and break it down. So first section, actually we're going to continue with the abstract for a second. Basically the what here is it's a dynamically assembled, temporally aware knowledge graph that maintains historical relationships. We talked a little bit about that. And we've got two outcomes. We're outperforming MEMGPT on the DMR and outperforming full context implementation on the LME. Full context implementation is really important. Essentially, this is context window stuffing. You're taking your entire AI memory and putting it in the context window, as opposed to building a system outside the context window that smartly hydrates the context window with a smaller subset of tokens. So we're going to focus on that here later in the talk. And then this is a visualization of a Zep graph. This is actually a pretty minimal memory set with only a few messages. And so you can see it gets pretty chaotic pretty quickly, at least from a visualization point of view. There's a lot going on. So the first portion of the paper kind of sets us up. It's the summary of the knowledge graph and how it gets constructed. So we have three subgraphs here. Number one, we have episodes. This is a non-lossy data source. This is my favorite part of Zep, actually. And so episodes contain raw data. They're actually messages, text, or JSON. This is really interesting because a lot of memory systems are lossy. And so because we're storing these episodes, which is the raw data source of where memories come from in this AI memory system, we can actually traverse the graph back to an episode from anywhere in the graph, which is very, very cool because we can get our non-lossy data representation of where this memory came from at any time, which not all memory systems have that characteristic. So that's my favorite part of Zep. From there, we have semantic entities. These are extracted from episodes. So if an episode is a message, we're going to take that message, we're going to extract what's called a semantic entity from it, and then we're going to resolve those semantic entities against the existing semantic entities in our system. If you haven't read the paper, that probably sounded like French. We're going to dig into that here more in a second. And then lastly, the highest level of graph in Zep is this thing called the community. There are community nodes that represent clusters of strongly connected entities, and they contain summarizations of the clusters. Again, it's the highest level of the graph. So we're going to dig into that at the end of the paper. Any questions up to this point? Okay, cool. So I drew a little bit of what Zep looks like, just to kind of lay out what they're talking about here. So at the bottom, we have our episodes. You can imagine these three messages sent to an LLM. We've got Alice started PapersWeLove last week. Bob joined PapersWeLove yesterday, and Alice and Bob met in NYC to discuss PapersWeLove. 3 messages sent to an LLM, and you can see via these episodic edges, we connect this episode up to Alice and Bob and PapersWeLove, and we connect all the episodes up to their semantic entities in the semantic entities subgraph. The semantic entities are connected to each other via semantic edges. So we've got Alice, the semantic edge started, to PapersWeLove. We've got PapersWeLove, semantic edge joined, Bob, and you go on and on. And from there, we go out to our community subgraph. Community subgraph, again, is the highest level of the graph in ZEP. We've got our community edges. So Alice is a PapersWeLove team member, and so is Bob. They're both PapersWeLove team members, and that's in the community subgraph. So you can imagine, with only 3 messages, we end up with quite a few edges. It gets pretty complicated as you build up a memory system, more messages over time as they go into the system, but remarkably it stays pretty organized and hydrates the context window well. Any questions here?
I'm guessing you get to this, but how does it turn raw inputs into semantic edges between objects up the next slide?
Yeah, we're going to dig into it. This is actually the core of like a lot of the AI memory systems, is we take these raw inputs like the episodes and we do inference on top of them. And the kind of differences in how you do that inference is what makes different memory systems kind of unique. And we're going to talk about how they do that in a minute.
So can those have multiple edges between them depending on if you get a new episode? You can imagine that there might be one more edge that comes up between these 2 rows.
You can, and they actually call that, those are hyper edges, and we're going to talk about those here in a minute as well. Yeah. Any other questions? Okay, cool. Okay, so episodes, again, my favorite part of ZEP. They are messages, text, or JSON, and importantly, they are bitemporal. So we have timeline T and timeline T prime. Timeline T is the chronological order of events. Timeline T prime is the transactional order of events. And this bitemporal nature of these 2 timelines of messages and really of graph of ZEP altogether enable ZEP's temporal awareness, and importantly, this is really where they get novel. So there was a system called GraphRag that existed. Really, ZEP is built on Neo4j too. This is a graph. But temporal awareness in graph was pretty unique at the time and is pretty unique, and that's really what sets ZEP apart. And we're going to talk about these 2 timelines, how they're different, how they're put into the system later, but for now, that's all you need to know. Messages have 2 timelines, timeline T and timeline T prime. And importantly, we can traverse the graph forward and backwards, so we can always get to our non-lossy data source from any node in the graph, which again, I think is very, very cool. Not all memory systems have that. Any questions here? Okay, cool. So our 2 timelines, again, the kind of most novel thing about ZEP, we've got like timeline T and timeline T prime. So timeline T is when the events occurred in chronological order. In actual real life reality, I got a dog, I went on a trip, and I started a new job. But when the LLM learned of these things from a sort of transactional order point of view, I told the LLM first that I started a job, then I told it I got a dog, and I went on a trip. When I gave it those messages, I somehow told it to that, I got a job 3 months ago. I got a dog 4 months ago. I went on a trip. You get my point here. It's actually kind of hard to illustrate, but the point is you tell the LLM, roughly I went on a trip 2 months ago. I got a dog 3 months ago. I started a job 1 month ago. And you can see how, even though the order is different from a transactional point of view, the chronological order, the 2 things differ. And ZEP is really, really good at this. ZEP assesses the chronological order as separate of the transactional order and uses an LLM to make sure that the transactional order, the chronological order, is kept intact. And so one of the kind of cool, interesting things about ZEP is this 2 timelines that it does. Any questions here? Cool. Okay, so going back to, if you imagine that graph that I had up, we had entities down at the bottom. In the middle, we have entities. They're semantic entities. These are entities. So they're generated by an LLM based on the current message and last n messages. In the paper, that last n is 4, so 2 terms. And we do some reflection to minimize hallucinations and improve extraction. And really all that is an agent reflecting on what it's doing via language, and that's used to guide the extraction process. And when we do the extraction, entity summary is generated. I did do a flowchart of exactly what happens when you derive an entity, or when you generate an entity or a set of entities. This is the most complicated part of ZEP. We could walk through it if you really wanted to. I don't think we need to. The net here is we take the episodes, we do a whole bunch of stuff to make sure that we're not generating erroneous entities, extra entities, duplicate entities, and we come to, at the end, the final new set of entities that we're going to add to the graph. That's the takeaway. I think generally these slides maybe get posted somewhere afterwards, so if you want to dig deeper into this, either come ask me or jump into the slides and we can talk about it. Okay, cool, yeah. Cool. So here we generate entities again with an LLM. Idea is that we don't generate duplicates, we don't generate, anything we shouldn't, and that the process you can see down here at the bottom is what helps us do that. Any questions? Okay, cool. So we found the hyper edge that you were asking about earlier. So this actually took me a second. When I read the paper the first time, I didn't really understand the concept of facts. Because they start talking about facts, but facts are not actually in the graph. And I had to really dig in to understand exactly what was going on here. Facts are a middle step. They're a natural language generation that happens between entity generation and graph integration. So the first thing we do is we pull out our entities. If our message is Bob went to New York, our entities might be Bob and New York. So that's the first thing we do. We have Bob and New York. The second thing we do is we generate a fact. It's a natural language fact. Bob went to New York. And so now we have 2 things. We have our list of entities, Bob and New York, and then we have our fact. And then those 2 things contribute to how we eventually integrate into the graph. And I can show that here. So we've got our fact. Alice, Bob, and Carol co-founded PapersWeLove. I'm sorry, guys. I know that that's not true. I was moving really fast and didn't have time to really dig into it. But here we go. So we've got Alice, Bob, and Carol as our semantic entities. We also have PapersWeLove as a semantic entity. Alice co-founded PapersWeLove, Bob co-founded PapersWeLove, Carol co-founded PapersWeLove. And this is a hyper edge because we have 3 edges connected to 1 node, PapersWeLove. Importantly, this is where we get into maintaining historical relationships. Carol left PapersWeLove. And so I didn't add the metadata here, but we would maintain Carol co-founded PapersWeLove, and we would also add Carol left PapersWeLove. And we use those 2 timelines to invalidate co-founded, but maintain left. And so the idea is when the LLM looks at this, it understands that Carol co-founded PapersWeLove and then left PapersWeLove. And it can understand both things, and that's how we maintain these historical relationships. So super interesting. Any questions here?
One question would be about, you mentioned they use an LLM itself to create a timeline of events, right? So have they validated how accurate is that if they try to extract a timeline using just an LLM? Right? That would be the first
one. So we're not taking an episode and doing a sort of arbitrary LLM generation. That's where this timeline, this flowchart comes into play. We're doing a lot of pulling things out and controlled. Then we're doing a vector search on the existing entities, and we're doing a hybrid BM25 on the existing entities. We're getting candidate nodes. There's a lot that goes on before we actually do a final generation of a fact or an entity, anything like that, or in the case of your question, the timeline itself. And so these systems, these multi-step systems, are how memory systems and maybe AI systems more broadly keep from the LLM generation being totally arbitrary. So I think we look at more detail, exactly how those timelines are generated, later in the talk. but the system is very similar. There are a lot of guardrails and steps to keep it from being an arbitrary decision.
One more question on that. You mentioned that there's multiple steps that are done by an LLM, right? So is there a possibility of cascading error, right? So if the first LLM at its first step makes an error, right? That cascades to the next step and then to the next step and so on. I don't know if that's something they've tested or if you've seen in person, while using Zep. But that sounds like one possible risk if you have many cascading systems of LLMs operating on the output of the previous step. Right? So is that
yeah, I think it is. I mean, it's the same as if you select the wrong token, you're more likely to select the next wrong token. I think it is definitely in the nature of these systems that they can make mistakes, and when you do make a mistake early in the chain, the mistake or a series of mistakes kind of proliferate through. I think, like I said, I think that's kind of the nature of non-deterministic code. Yeah.
In the next slide, you mentioned that the facts are independent of the graph. Is there a reason for that? And like the way you have presented it there, the edges are sort of facts for the graph. Right? So
yeah.
Why are they two different?
So this is the thing that took me a second to really grok when I read the paper, because facts they get stored, but they get stored as metadata within the edges. So what we're doing is we're generating this fact. Alice, Bob, and Carol co-founded PapersWeLove, and then shortly here we're going to see how we actually generate the edges. So we generate an edge, co-founded, and we attach in that metadata Alice, Bob, and Carol co-founded PapersWeLove, and then we actually vector embed that as well, so we can query against that in vector similarity search, which is kind of interesting. So there are many different ways you can query the graph, but we'll get to that too. But that's how you end up with a fact that then gets translated into an edge. So you get your entities extracted, in this case, Alice, Bob, and Carol, and actually PapersWeLove. And then you get your facts, and then based on the fact and the entities, you generate your edges, and you integrate all of those into the graph.
And you can derive facts back out from the edges, basically. Right?
Yep, exactly. So the facts, like I said, are stored on the edges and accessible either via vector similarity search or BM25.
So if you queried about Carol.
Thank you. Okay, so is the purpose you said that the fact is stored as metadata for the edge. So if you queried, you talk about retrieval later, but if you query and you retrieve information about the entity Carol, do you then, because the edge just says co-founded PapersWeLove, but that co-founded edge has the metadata Alice, Bob, and Carol co-founded PapersWeLove. So if you were trying to hydrate the context window of an LLM with the context querying Carol, would it also have the information about Alice and Bob? Is that why the fact is stored there, or is there some other reason?
That is why the fact is stored there. So if we flip back really quick to the actual result of the Zep, this is an actual result of Zep hydrating a context window. The first time I saw this, I thought, this is crazy, there's no way this works. And then I started working with it, and you realize that hidden in here is all the information you need to make an informed response. And so it's kind of cool because the LLM has the information that Carol co-founded PapersWeLove, but it also has the broader context of who Carol co-founded PapersWeLove with through that fact. Yeah.
Makes sense.
Cool. Any other questions? Okay. This, I think, is just another look at generating, here we're generating up to an edge. So we've got our episode, Alice moved to Paris, any ideas for housewarming gifts? This is a message someone sent to an LLM. Our semantic entities, Alice and Paris. Our fact generated, Alice moved to Paris. And then this is actually where you can see how the fact is stored on the edge, excuse me. So we've got our edge, our relationship type is moved to. Our source entity ID is going to be Alice, Alice's ID. The target entity ID is going to be Paris's ID, excuse me, and then the fact is stored on the edge. Alice moved to Paris in 2022. We also have validat and invalidat, and we're going to dig into that. That's part of the sort of bitemporal timelines, so we can talk about that more in a minute. Any other questions here? Cool. All right. Edge deduplication. So like I said, there's a lot of systems built into Zep to make sure that the graph stays, I think, stable and doesn't get out of control. One of the interesting things about Zep is that the graph is sort of arbitrarily built over time. And so I think they're doing a lot to keep it from getting out of control, and edge deduplication is one of those things. So we embed our facts into vector space, and then we do a hybrid search on the existing graph. Number one, we look for similar edges between the same source and target nodes. So if we've got Alice and Paris, we're going to look for similar edges between Alice and Paris that already exist in our graph. And we're going to do a second search to find all similar errors for contradiction detection. And then we're going to give all of that to an LLM. And the LLM is going to perform deduplication and contradiction detection. So any duplicates that we have, it's going to deduplicate. And anything that contradicts, anything contradictory is going to actually supersede the old edge or memory with the new edge. And so that's one of the ways kind of the graph stays up to date. If Zep gets contradictory information, if you send a message today that contradicts what you said yesterday, Zep always prefers what you said most recently. So Zep will overwrite the previous memory with the new memory. Any questions on edge deduplication? There's another flowchart if you guys really want to dig into the slides, which sounds like it'll be in the Discord.
Does that search for similar edges, I guess, between any nodes, right? Is it repeated?
That search for similar edges, I guess, between any of the nodes, done based on the embedded facts, I guess? And is it the fact that's embedded or the entire edge?
Yeah, so this is done in vector space. So it's based on the embedded fact. Yeah, and so we're doing two searches. Number one is a scope search to only the nodes we're searching, the source and target nodes. And then the two is the search across the entire graph. Yeah. Any other questions? Cool. All right. Temporal extraction and edge invalidation. More ways we're keeping the graph under control. And this is where you end up with T and T prime, the two timelines and how this works. So number one, when an LLM is asked to extract the chronological order of events. So we get a valid at, which is a fact, when the fact became true chronologically. And we have an invalid at, which may or may not be populated, which is when a fact stopped being true chronologically. So if I went on vacation last month, I was in Japan for 2 weeks, and I'm no longer in Japan, I'd have an invalid at for the memory I'm in Japan. Rylan is in Japan. But if I live in New York City, that's still true. I would not have an invalid at for I live in New York City. So that is how we get chronological order. The system sets transactional order. So created at is simple. It's just database ingestion time. And expired at is when the edge was marked expired. So if the edge was marked invalid at today, that expired at is always going to be today, even if the invalid at is a previous state, because again, we've got two timelines happening. That also took me a second to fully grok. It's a little confusing until you really start to think about it. And then lastly, invalidating old facts. New facts can invalidate old facts via that LLM comparison we talked about. A contradicted edge will have an invalid at set to the contradicting facts valid at, and expired at set to now. So that kind of clarifies how we end up with how expired at is set. So we talked about the two timelines. This is just, we have two facts, and we do a comparison. The comparison finds that there's a contradiction. We invalidate the old fact. We take the new fact again because we always take the most recent fact when we end up with contradicting facts. Any questions here?
What assumptions, if any, are made about the input data? Because how do you always have the valid at?
It's a good question. Do we always have a valid at? I actually don't know the answer to that question. Whether valid at must be populated or not, I'm not sure. So I don't want to give you an answer I don't know. Yeah.
In general, though, is there an assumption about the inclusion of a time to construct any chronological order, or is it like?
There's not like a general assumption, as far as I know. Really, it's looking for, it may be when the LLM receives the memory for the first time. I really didn't dig into it. That's actually a really good question. Yeah.
Last little, I have invited, we'll try like best guess and for like a relative order, like make up like numbers or.
I don't want to, again, I don't want to give you an answer I don't know, so, yeah. Any other questions?
I'm wondering what might happen if the facts aren't true that are added, or maybe there's some misunderstanding, like Ryan is in Japan, but maybe you have a delayed information from the airline that says Ryan didn't check into his flight to Japan.
Yeah. So if you end up with information introduced to the graph that isn't true, the graph has no way to know, and the memory system has no way to know that it's not true. So again, to your question about like, can the graph kind of drift off course, I think that the answer is yes, and that's one of the ways. So if you introduce information into the system that is, totally not factual, it will remember information that's not factual.
Garbage in, garbage out.
Yeah. Any other questions? Cool. All right, so the highest level of ZEP is the idea of a community. So communities are assessed during entity node graph integration. They do so via label propagation algorithm, which allows it to happen in real time and without recomputing the entire graph, but does over time mean that we drift away from true clustering. And because we drift away from true, ZEP actually in the paper recommends periodic refreshes of the community nodes, essentially, of the community associations, excuse me. So new nodes join their neighbors without recomputing the whole graph, like I said. And upon community addition, we actually have a community summary that we regenerate. And so this is actually an easy flow chart for us to look at. We go update community. We determine the entity community by finding the neighbors communities. So the nodes that are near the new node, we find their neighbors and we find their communities, excuse me. And then we pick the most prevalent community. We then summarize the entity and the community, and we update the community name, and actually add the new node to that community via those community edges that we looked at earlier. So this part's not too complicated. Any questions here?
Why is this notion of community is important at all in the construction of ZEP? Is it necessary for doing retrieval from the graph? Does it serve another larger purpose in how ZEP operates itself?
It's for retrieval. Yeah.
Retrieval.
Yeah.
Okay.
Any other questions? Retrieval too, and I think also when you hydrate the context window, you can hydrate, for example, if you go back to PapersWeLove members, the LLM has this notion of PapersWeLove members and a summary of what PapersWeLove members actually is as a community. And so I think it's retrieval, but it's also too in the generation process, giving the LLM a really rich context of what's going on. Any other questions?
So this is more of a general question on this slide, but for the, I was wondering, has there been any discussion about sort of the order that you present information so that you kind of prime entities initially with the types of entities that you want to, have show up in the database later? Is kind of one question, and a sort of related one is there a way to kind of manually insert entities and edges from more structured data you might have, like out of like a code base and like dependencies between things, rather than just hoping an LLM will pick those up?
Yeah. So to answer your second question, is there a way to add structured data? The paper specifically focuses on messages, but you can add, I believe it's text. I'd have to go back and look at the types, but at the very least JSON, and I think that's the important one, but it's not highlighted in the paper. as far as is there a specific way you want to input information into ZEP in order to sort of control what's remembered and how. I think ZEP is really designed to listen into conversations and to build memory over time. It's less, as far as I understand, and maybe there are implementations and uses where this is the case, but at least ZEP, as it's described in the paper, is really about building a memory of who a user is, how they're using a product over time as they chat with an application, as opposed to, I have a corpus of 5,000 messages, I want to put those into ZEP. I'm sure there's a way to do that. I'm sure it's been implemented either by the ZEP team or others, but specifically what the paper is focused on is sort of building a memory over a conversation. Any other questions? Cool. All right. So that is ingestion. All AI memory systems really have two parts, ingestion and retrieval. So we'll jump over to retrieval. Retrieval is pretty easy to wrap our head around. So it's 3 steps, search, re-rank, and construct. We start with a query string. This is typically a user's message, and we end with a context string, which is that big block of context we were looking at earlier. So like I said, 3 steps. We talked about our input and our output. We take that context string and we concatenate it with the prompt. We put that into the LLM. We make our LLM call and we get our LLM response. And this is a memory-informed response as opposed to one that's not. So what that looks like, if we go step by step, starting with memory retrieval search. So search transforms our text query into a 4-tuple. We specifically have edges, entity nodes, community nodes, and episodes. And we do this via parallel searches across all of our graph layers. We've got a cosine similarity search at BM25 and graph traversal. There's a little note here. The paper claims that it's a 3-tuple. The code base, the open source code base right now is a 4-tuple. Maybe it's evolved, I'm not sure. This is what the graph of what that looks like. We take our text query, we do our 4 parallel searches, and we end up with our 4-tuple result, edges, nodes, episodes, and communities. From there,
Before you go on,
yeah, go.
for those who don't know, what is BM25?
BM20.
That's honestly, I am not in this space. What are
Yeah. So BM25 is just, as I understand it, plain text search. And then cosine similarity is vector search. So we embedding whatever we're searching for into vector space. We have vectors that are in vector space, and then we can query the vector space for semantic similarity.
That's the classic word to vector style.
Yeah.
Okay.
And then the graph traversal is we can move from anywhere on the graph sort of forward or reverse, and that's how we get to the non-lossy episodes, for example, which, as I said, is why I think stuff's so cool. Yeah. Any other questions? Cool. All right, so from there we go to re-ranking. This reorders the 4 search results of our search result from the prior step. Each has its own sort of approach as defined in the paper. Edges, nodes, episodes, communities are all re-ranked differently using different approaches. And we do these in parallel as well. So we get our 4-tuple result from the prior step, and then we do parallel re-ranking. And so we take the results of the prior step and we say, based on a number of criteria, put these in the correct order, where at the top is the most relevant information, at the bottom is the least relevant information, and the end result is a new 4-tuple that contains the same information but re-ranked. And so now the information is in order from most relevant to least relevant. Any questions here?
This may be my ignorance about how prompts work. You want it in order of most relevant to least relevant, and then you inject the next prompt, and then you have it continue generating text. Wouldn't you want the least relevant stuff the farthest from the next generation token?
Really, I think in an LLM, so the information at the top of the context window and the information at the bottom of the context window, much like a human, like when we read a book or something, those are the pieces of information that we notice the most, and LLM is actually the same way. As far as re-ranking, so often in systems, re-ranking also disqualifies results. Yeah, and so in researching for the paper, I didn't see a disqualification step. It's very possible because it's a normal characteristic of re-rankers that we disqualify results as well. So it's possible that in the 4 tuple results in the middle, there are more results than those results that are at the end. Any other questions?
Are all the re-ranking algorithms, are all those like kind of generally fast algorithms, or do those also use LLMs?
Many of them do use LLMs. And honestly, many of these I'm not super familiar with as far as like getting up close and personal with them. I was doing a little bit of reading before we came. There are interesting ones like graph proximity to the center node. Like that one's pretty cool because it's like very ZEP specific. But often there's re-ranking that's just purely LLM as well. And so as I understand it, they're kind of deploying a number of techniques here. And like I said, I didn't get too up close and personal with them, but they're definitely doing a lot as far as re-ranking is concerned. Cool. Any other questions? Cool. All right, so this is the last step of retrieval. It's the simplest part of retrieval. We're going to take our 4 tuple. We're going to construct them into a sort of final context block. We've got our edges, which have temporal relationship data, entities, which have entity descriptions, episodes, which is our original conversations like we talked about, and then the communities and the summary of the communities. So to answer your question earlier about the relevance of communities, we're actually putting those into the context window with the summary, which is where we get sort of rich context for the LLM. And we've looked at this quite a bit already, but this is what the end result of ZEP looks like. I could not fit it all into the slides. There's an ellipsis here. There's a lot more to it. But you can imagine that if we're adding this to the LLM's context window on every call, it has a lot of information that it otherwise wouldn't have. And so that's where you really see ZEP shine. Any questions here? Cool. So last section of the paper is experiments. As I mentioned, ZEP tests itself on 2 benchmarks. Number 1, the Deep Memory Retrieval, DMR, and number 2, the LongMemEval, LME. These are, in my mind, 2 of the most relevant benchmarks in AI memory. Glad to see them here. On the DMR, ZEP does not perform very much better than full conversation context. And so this is really, really interesting. At first glance, you're like, well, why do I need ZEP if I can just put the entire conversation into the context window? And we'll talk more about why you need ZEP, even though this is the case, but still very interesting that you can get the same results as ZEP by just putting everything into the context window. And we're going to talk about why there's more to this here in a second. So the second thing they did was they ran ZEP on the LME, the LongMemEval. Here you see the difference between ZEP and the full context technique. It's more readily apparent. So number 1, this LongMemEval, the conversation length average is 115,000 tokens, which is more than the Deep Mem, the DMR. And so on longer conversations like this, we do see that ZEP actually outperforms the full context technique using GPT-4o and 4o mini. So it's a 17% increase. But importantly, and this is really the benefit of ZEP, we have a 90% reduction in latency, and we also have a 98% reduction in the number of tokens we use in generating these results. So saving tokens, saving cost, and if your application is something that is sensitive to latency, you've got a lot lower latency. So though these numbers don't look great, what's really going on here is we have the same quality results, but we have much lower latency and we have lower token costs. Any questions on these 2 slides?
What's driving the increased latency in the case of full context unit? Because that is an entire workflow that involves retrieval and creating the context. So, I mean, how exactly is full context being used here, and what is causing it to be so slow?
Yeah, so full context is taking all of those 115,000 tokens and putting them into the context window to make your LLM call. And so the LLM actually has to process all 115,000 of those tokens to make its generation, which is why you see such a big increase.
So then latency and average context tokens are related here.
Yeah. Any other questions?
Is Zep's retrieval latency also included in this?
It is, yeah.
Wouldn't be very fair on the
Yeah.
We hope so. Any other questions? Cool. So again, thank you, Nathan, for this. We've got, you can't see it actually, but this used to say context, text, and subtext, but in the projector, it's too hard to see. So I want to talk a little bit about subtext, sort of my thoughts on the paper. So the paper was published in January 2025, which sounds recent, but in this world, it's definitely not recent. It's, yeah, a lot's changed. So what has changed? In February 2025, we got Claude Code. That doesn't sound related, but it is, because with Claude Code, we saw the first glimpses of what an AI managing its own memory system sort of agentically looks like. That's really interesting, so we'll talk more about that here in a second. April 2025, we got MEM0, which is sort of another, at least commercially speaking, leading architecture competing with ZEP. And then May 2025, I mean, the models have always been getting better, but we got Sonnet 4 in May 2025, and in August 2025, we got GPT-5. So a lot has changed. There's about a million other things, as we all know, that aren't on this slide, but just highlighting a few things between now and January 2025 when the paper is published. So if we dig a little bit deeper into this, the paper tests ZEP against GPT-4o. GPT-4o has a context window of 128,000 tokens. On a benchmark long context reasoning, it performs at a 53%. It costs $2.5 per million tokens, and average latency is 0.8 seconds. So I want to compare that with GPT-5, and we'll see why here in a minute. But GPT-5 has a context window of 400,000 tokens. On that same LCR benchmark, scores a 76%. We get an input token cost that is half the $2.50. We're down to 125, and our average latency is not much more at 1.04 seconds. So context window size increased by 212%. On LCR, we're up 43%. Token costs are down 50%, and latency is up 30%. So some good, mostly good, and the latency obviously has increased. So when we look at ZEP versus full context, again, full context is just dumping everything into the context window, not using a memory system. Again, if we go back to the scores, ZEP was 17% better from a quality point of view, had 90% better latency, and from an average token cost point of view was 98% better as well. So ZEP still presents benefits. We've got cost savings and low latency, but due to model advancement, models are beginning to get really, really good at managing their own memory. And so this idea that ZEP is going to do better from a quality point of view over time as models get better and the architectures change, that's an interesting question, but definitely from a cost saving point of view and latency point of view, we still have benefits. And so I want to talk a little bit about how memory architecture has evolved since January 2025. This is like my favorite blog post in the world right now. It's a reverse engineering of ChatGPT's memory. And I just think it's really, really interesting what they're doing. They've got a 4-layer memory system at the top. They've got like your device info, usage patterns. From there, they've got your recent conversation context. This is one of the most interesting parts. It's like 40 chat histories. So it's an enormous block of just, if we go back to ZEP, this idea of episodes, the actual context from your conversations. From there, we've got model set context. So this is memories as we understand it. I'm allergic to shellfish. And then lastly, we have user knowledge memories. This is another one of like my favorite parts of this architecture, which is these dense AI-generated summaries of hundreds of conversations. And these are generated via offline jobs. And so what ChatGPT is doing, at least according to this blog post, which is a reverse engineering, so could be wrong, but as far as we could tell, or this blog post could tell, it's just dumping all of this context into every LLM call, which is remarkable. So essentially what they're doing is, because GPT-5 is so good at parsing long context, they're saying we're going to put your personal memory alongside your engineering preferences and everything, and we're going to actually trust the model to find exactly what's relevant every time it makes a call. So I think super cool and super interesting, and a very different approach to what Zep's doing. So last thing I want to highlight on sort of what's changed is another architecture, the Claude and Claude Code architecture on AI memory. This one's a little easier to read. We're not reverse engineering anything, but this is basic. This is a file-based tool system. If you've used Claude Code, you've seen it in action. I think it's pretty magical. And essentially what we're doing is allowing the LLM to use tool operations to read and write its own memory files. So very different from what ChatGPT is doing, but also too very different from the Zep approach. And so trends in AI memory, we're seeing simpler architectures, and more than anything else, we're seeing models getting smart enough to really manage their own context, either agentically or via long context reasoning. But we still have drawbacks, and we still have benefits to something like Zep. Zep, the memory trends result in increased latency, increased token costs. Zep, you get your reduced latency, you get your reduced token costs. So I think this architecture is still really relevant and very cool, but I did think it was worth highlighting sort of how things have evolved, because it's changed very fast even since January. Any questions up to this point?
It occurred to me that this comparison between full text and Zep may not actually be fair, because you could just build a retrieval system on top of the full context, right? You could retrieve the relevant portions of the episodic memory, and then you could feed that in, right? Is the only thing that's driving the latency is the fact that you're feeding in a significant amount of context. You could just build a simpler retrieval system than all of the machinery within Zep, and that could potentially save up on the context tokens as well as the latency. So it still leaves open the question of what is the value add of Zep if potentially a simpler retrieval system could also do a potentially similar job.
Yeah.
I don't know if that's something they have evaluated or someone else has evaluated.
I think really everyone in the AI memory space is interested in this question. How complicated these systems really need to be? Does something like RAG over your context work if RAG gets really good? Does BM25 over your context work? Does the ChatGPT or the Claude architecture work? Like, there are so many interesting questions, and I guess what I wanted to highlight here is how much things have evolved. And as the models get better, we're seeing the memory architectures change really fast. I think we got a few more.
How does this change if the model is local and I have an infinite context window and it's just like on my gaming laptop?
Yeah, if the model's local, is your context window truly infinite? I have not spent a lot of time with infinite. If the context window is infinite, I mean, it's awesome. I mean, also too, the LLM needs to be able to parse what's in its context window. So it's not just that the context window needs to get bigger, but the LLM needs to be able to actually handle what's in its context window, which is why you see the big jump in the LCR from 4.0 and 5 being really relevant to memory. Is like you can now put information into the context window and let the LLM actually figure out what is relevant. So I think that's going to be model to model, case by case. But the ability to put a lot of information into these context windows is definitely something we already see, and I think we're going to see a lot more of.
Why do you think the model builders haven't pursued like graph-based memory architectures when they implemented their own memory?
I think the question is interesting. I think in the case of the most recent architectures, I think they're finding that the models themselves don't need a graph-based architecture because they can manage their own context really well. So it may not be necessary to put a graph on top of your memory system if you can manage either via long context reasoning or an agentic workflow like Claude Code.
Do you know if there's been any work on, like, as newer models come out to kind of incrementally or from the beginning, like, rebuild the graph? Because, presumably it could extract better relationships and enemies and sort of thing.
Yeah, I actually think it speaks to your earlier question, like what work's been done around ingesting a corpus of existing data with Zep. I have to imagine, at least commercially, they have a way to do that. They are a company, so I've never worked with a system that does it. The paper doesn't cover it, but whether it's Zep or someone consuming their open source library, I'm sure someone has done it. And I think in that scenario where you do have a way to ingest a corpus into a Zep system, you could do that ingestion anytime you wanted to, including when a new model came out.
The paper does mention that it needs to redo the communities at one small, right?
It does,
So
yeah.
it must be it's really contemplated by the code that you would need to reparse the entire graph.
Yeah. Any other questions here? Okay, so why AI memory? This is actually maybe a little bit sappy. I'm just interested in this stuff. Why me personally, but maybe more broadly, why is this stuff interesting? I think AI memory and maybe AI broadly, but AI memory certainly, we've got computers that are starting to understand us and evolve with us over time. You imagine that they could accumulate context on us, over a lifetime. Persist that context across applications and devices, which we can't do today, and that really disappoints me. And these computers can feel deeply personal. You could imagine a second brain of the knowledge we accumulate, and that this second brain could be really tuned to our personalities, our working styles, our preferences. And then it opens up really interesting sort of existential questions, like what happens to a lifelong AI memory system when we die? Could a digital version of us live on? And would we want it to? I know it's a little sappy, but these are the kinds of things that get me really excited about where we're going, and definitely the reason I'm interested in AI memory. So yeah, that is everything I've got on Zep. Any other questions?
I'm going to use host prerogative to speak for a second first. I found it really interesting. It mentions the bitter lesson in that blog. I didn't read the blog post, but just from the title. If you're working in AI but you haven't read the paper, it's really a blog post more than anything, the bitter lesson. Highly recommend you look into that. It basically goes, the bitter lesson of 50 years of AI, 75 years of AI work is just throw more hardware at the problem. And so seeing that playing out here with the Zep feels very influenced by a lot of the sort of old school AI techniques. So we're going to do graph knowledge, we're going to do all these sorts of, trying to model the world. And then GPT-5 is no, just give me everything. Just throw more code into the problem and solve it. That's a very interesting result to see. Okay, now that I've done that, you have questions?
It's interesting you mentioned that article. The article is by Richard Sutton, I believe, right? The better lesson. It's by Richard Sutton, I believe.
I may be true, I don't know.
Yeah. He's the author in case anyone's interested. So a question about Zep. The last slide talked about how you might accumulate memories over an entire lifetime, right? So thinking about Zep itself, what would you say are the bottlenecks as it gets more and more episodes, right? Is there a specific component of it that might get bottlenecked? Would it, for instance, be memory limited, right? Or would it be limited by retrieval, like beyond a certain amount of episodes, maybe retrieval becomes way too slow, maybe it's a different component of it. I'm just wondering, in a graph-based architecture like Zep, what would be the limiting component that would prevent it from going past a certain point?
Yeah, I don't want to give you a technical answer because I've never deployed Zep at huge scale. And I think that's when you would start to understand technically where the system breaks down. But you could imagine a world where the graph itself gets out of control because it's arbitrarily defined and created in real time. And so I haven't seen that play out, but that is one thought that, hey, this could does this work over extraordinarily long horizons, or does it really start to become messy, and do our results become lower quality? You know?
I have a question about the episodes. So typically, with AI, a lot of them are like chatbots, so it's not just like one message that you would kind of try to extract fact from, but it's like a series of back and forth, and you'll put the entire previous part of the conversation as your initial context. Does that also happen when the episodes are stored in their raw form? Like, is it kind of like every single message you send to the LLM includes the full context, so you're kind of like duplicating the prefix constantly?
No, it's local to the message. So if you had a series of 50 messages back and forth, the episode is the message where that memory was derived.
It's just the string you typed in.
I had a question about the retrieval step. You said the facts would be used to like generate, or like gather other related information, right? Is there like a recursion to that as well, where you look like any deeper? For example, like you're asking about like Rylan, and Rylan's related to like Kenny in some way. It's like, do you pull up facts related to Kenny, or then like Kenny's connections, like?
Yeah, so the ZAP queries are configurable, so you can set different parameters on how deep into the graph and how far you want to go and what you bring back. So I think that's the way you would do it, is by kind of tuning the query side, the configure the params on that side. Yeah.
Yeah, sorry, a follow-up from the previous question. So if it would be only inserting the message the user typed, and the user said, like, I picked option 1, right? And option 1 was kind of mentioned in the previous. Does Zep take that into account? Like, would it know what option 1 was?
Yeah, when it does its generations, it generates with the message minus n, and that minus n is the number of messages prior that you're going to give to let the system do its generations and assemble the graph. The paper dictates that that's -4, so n is 4 in that scenario. They sort of baseline it like the message and then 2 prior turns, agent assistant, but that is also a configurable value.
All right, I think that just about wraps it up. Thank you so much for that talk. Very good. Give them a round of applause.